Hello everyone! In this video I'm going to talk about orientation of coordinates. The problem is that often there exist 2 or 3 equally good choices of coordinates orientation for a particular symmetry group, and they lead to different irreducible representations. In this example we see water molecule, C2V, the z-axis is always along the principal axis, but then we have a choice. We can place the water molecule in the yz or xz plane. Another example can be ethene, D2H. There are 3 equally good orientations of coordinate system, since we don't have a principal axis. All axes are C2. The obvious question is, does it matter? And the short answer is no, it doesn't. But if you don't make your choice of coordinates clear to your examiner or lab supervisor, it can cost you marks. So to elaborate, if you have a choice regarding orientation of axes, then whichever you pick, it has no consequence to the MO diagrams or the number of predicted vibrations. But because different choice of coordinates leads to different irreps, always label your diagrams. Otherwise, you make your lab supervisor guessing, and he might not be in the mood of guessing, okay? Also, don't freak out if after solving a question you realize that the solution manual shows different irreps to the ones you derived. The first thing to check in such situations are coordinates. Having said that, usually authors do tell you what orientation of coordinates you need to choose. So in the next part of the video, I'm just going to show you what I have just said on specific example of CH stretching vibrations of ethene D2H. And by the way, this video might seem like a jump into deep water because I will be doing some stuff that we have not spoken about yet, but all I would like you to do is to look as I am solving problems using different orientation of coordinate system and observe that it does not affect vibrational analysis. So first, let's place ethene in a ZY plane. Let's place vectors along the CH bonds, since we are only looking at the CH bond stretching vibrations, and let's write the reducible representation. We use 4 basis vectors, that means the matrices for reducible representations are 4 by 4. We ask, do the vectors stay put or change place? It's because only the vectors that do not move will contribute to the characters of the matrices that we are interested in. So all 4 vectors stay unchanged under E operation and sigma yz. Next, we need to break the reducible representation into irreps. We discussed reduction formula in the previous video, it's very easy, but to remind you, you need to multiply the number of elements in the class by character of corresponding reducible representation and the character of irreducible representation that you suspect is present in the reducible representation. You need to do that component-wise, sum it up, and divide by the number of elements in the group. So the reducible representation breaks to AG, B3G, B1U, and B2U. Now let's do the same for ethene in XZ and XY plane. Now is the important bit. Let's see how many stretches we can expect from IR and Raman spectra. We have not spoken about it yet, but a vibration will be IR active if it belongs to the same representation as one of the functions x, y, or z. And if a vibration belongs to the same representation as any of the quadratic functions, it will be Raman active. So we see that regardless of the orientation of the axis, we always get the same number of IR and Raman active vibrations. Now let's see how these stretches look like. To find out, we will use projection operation method. We need to construct symmetry-adapted linear combinations of basis vectors. I am aware we have not discussed it either, but this is the recipe. Let's label the basis vectors, then we need to take one of them, let's say R1, and we write down where R1 will end up under all symmetry operations, and we get this. Then we take this outcome and multiply component-wise by the entries of the irreps that describe the stretching vibrations. For example, for B3G, we will multiply R1 by +1, R2 by -1, etc., and we get this. We need to do that for all relevant irreps, then we need to get rid of the common factor 2, and then let's normalize the vectors to the length of 1. These are called symmetry-adapted linear combinations of basis vectors. Now we are ready to plot the vibrations. A vibration has the same symmetry as the irrep that describes it. The top irrep is always fully symmetric. Here is the AG irrep. fully symmetric stretching vibration corresponds to all bonds stretching out at the same time. The rest of the irreps and hence vibrations have lower symmetry. For example, for B2U irrep, we have -R2 minus R3, and that is telling us that we need to flip the direction of R2 and R3. The way we interpret this stretching vibration is that the bonds that we marked as R2 and R3 are getting shorter at the same time as R1 and R4 are getting longer. Notice that the resultant vector of these four vectors would be pointing in the y direction. That is because y vector, or y function, depending how you would like to think about it, has the same symmetry as B2U. So how does stretching vibrations look like when we choose different orientation of coordinates? Well, let's look at B3U. If you do the same type of analysis, you will find that B3U looks like that. It's identical to B2U, but this time, because the molecule itself is in the zx plane, so the resulting vector is pointing in the x direction. The physical reality of these two vibrations is, however, identical. To sum up, for D2H, each of the three different orientations of axis result in stretching vibrations that look the same, but some of them are just simply oriented along different axes because the orientation of the entire molecule is different. So that's all I have for you today. Thank you for watching and see you in the next video. Bye!